Yesterday we defined momentum. There were two ways in which we defined momentum. One was the real scientific way of defining momentum, and the other was just a way that we think of momentum that, to be honest, I think is a better way to define it because it helps us to understand it a little bit more than the actual definition does. Who can give me one of those definitions, whether it's the real official way of defining momentum or whether it's just the way that we think of that I gave you yesterday? I don't care which one it is that you give me right now, if you can give me either one of them. Good. Okay, momentum is the product of mass and velocity. That is the actual definition of momentum. If you're ever asked to define it on a test or a quiz, that is the definition that we want to see, the product of mass and velocity. And of course, that ultimately leads to the equation P is equal to m times v. What's the other way we defined it? The way that helps us to understand momentum a little bit better. Yeah, it's how hard it is to stop something. Okay, the difficulty in stopping something. Let's focus on this one for a second. How hard it is to stop something. What's another term that's a lot like momentum that has a definition that's real similar to that? Not how hard it is to stop something, but rather how hard it is to change the motion of something or the tendency of an object to maintain its current state of motion. What's that other term? Inertia. Momentum and inertia are not the same thing, but they're real similar to each other. What do they have in common with each other? What's the one thing that momentum and inertia both have? They both have mass. Yeah, if an object has mass, it has momentum. Well, at least it potentially has momentum. It needs mass in order to have momentum. If an object has mass, then it's also going to have inertia. What does momentum have that inertia doesn't have? Velocity. So in other words, momentum depends upon both of them. Inertia only depends upon mass. That means that an object that's moving has both inertia and momentum. An object that's at rest has only what? It has only inertia. Does the object at rest have less, have more, or have the same amount of inertia as that same object does when it's moving? It's the same, because its mass is the same. Does an object that's at rest have less, or more, or the same amount of momentum as that same object when it's moving? It has less, because of course it doesn't have any velocity. In fact, what would its momentum be as it's at rest? Its momentum would be at 0. Its inertia would be exactly what the inertia was when it was moving. All right, let's go back to this equation now for a second. P is equal to m times v, the real definition of momentum there. What units do we use for mass? Kilograms, right. What units do we use for velocity? Meters per second. So the units for momentum would be kilograms meters per second. A real common conversion that we have to do here is kilometers per hour to meters per second. Who remembers how to do that conversion of kilometers per hour to meters per second? Rob? Let's divide by 3.6. Now, if you're anything like I was when I was in high school, I was terrible at remembering these things. I could remember the number 3.6. That was easy. But remembering whether to multiply or divide and when I multiplied and when I divided, that was my problem. I would always forget that. Hey, some of you guys are a lot better at remembering those things than I ever was when I was in high school. How did I end up remembering it? Well, I didn't really. Basically, I would think I knew the answer, and then ultimately, though, when I had to do it, I'd guess. But when I guessed, I always checked my guess. Is it reasonable? Let's say we've got a speed of 100 kilometers per hour. Okay, that's the speed, almost the speed limit on the highway. Cars traveling down the road at 100 kilometers per hour. We want to convert that to meters per second. Do we multiply by 3.6 or do we divide by 3.6? Well, let's guess multiply. What do you end up getting? 100 times 3.6 is 360. 360 meters per second. 3.5 football fields per second. Is it reasonable that you, as you're driving down the highway in your car, are traveling the length of 3.5 football fields every second? No. So it's not multiply by 3.6. I guessed wrong, right? It's divide by 3.6. Now, if you can remember that, that's great. But if you can't remember it, then it's okay. Guess. Just make sure you check your guess. Even if you think you remember, it's always a good idea to see if your answer is reasonable, just in case you think you remember it, but you don't really remember it. You divide by 3.6. If I wanted to go meters per second to kilometers per hour for whatever reason, what would I do? I would times it by 3.6, multiply it by 3.6. All right. What's this little arrow over the momentum sign mean? It's a vector quantity, right? It has direction associated with it. And it must, because it's the product of mass and velocity, the product of a vector and a scalar. Whenever we do that, we get a vector quantity. So scalar times the vector, mass times velocity, always gives me a vector. All right. Let's take a look at the answers for the homework questions that we had last night on our worksheet. Take about 30 seconds or so and look at those answers and make sure that you either got the right answer or that you put up your hand and tell me which ones you need to go over because you got the wrong answer. If you happen to get a correct answer, but you're not sure exactly why you got the correct answer, then put up your hand for that one as well. And we'll go over whatever we need to go over, okay? Yes. Which ones do we need to go over here? My guess is we're going to have to go over 7. Is that right? Yes? Any of them beyond number 7? 8? Anybody for 8? 5? We got 5 and 7. 8. Going once? Going twice? 4? Okay, let's take a look at 4, 5, 7, and 8. 4 says a 75-gram ball is rolling at a speed of 57 centimeters per second. Calculate the ball's momentum. This is a pretty straightforward question, except for a couple of little things that we can easily overlook. My strategy when I look at a fairly simple question like this, but that has a couple areas where I can make a silly mistake, is to draw attention to those areas. Now, I normally want to circle my givens or at least write them down, but here I'm going to draw special attention to these two things. Why have I drawn special attention to those two things? Why have I circled those in red? It's not the most important part of the question. The most important part of the question is the general strategy, and I haven't even got there yet. But why have I drawn special attention to those two little things? Dan? They're not the standard units. I can't tell you how many times I've seen people make silly mistakes on tests, or on diploma exams for that matter, because they just forgot to convert grams to kilograms or centimeters per second and meters per second. I did a little poll once after a unit test a couple of years ago, 25-question unit test. On average, everybody in the class made 2 silly mistakes like unit conversions or something like that. 8%. On average, everybody in the class lost 8% because of silly things like that. So we have the opportunity to draw attention to it. Let's draw attention to it so we don't forget to do those conversions. All right, I'm going to say that the 75 grams is the mass. I'm going to say this is the speed or the velocity. We want to find the momentum there. Momentum, of course, is m times v, but we've got to do that conversion for mass. How many grams in a kilogram? Anybody ever forget those conversions? Sure, sometimes we do, right? Take a look at the 3rd page of your data booklet. Or the 2nd page, sorry, of your data booklet. The 2nd page of your data booklet. In the middle of the 2nd page where it says physics data sheet, it gives you the metric prefixes. It tells you that there is 1,000 grams in a kilogram or 1,000 in a kilo. It tells you that there's 10 to the minus 2 in a centimeter or a centa prefix. So if we have 75 grams and there's 1,000 grams in a kilogram, let's divide by 1,000 and end up getting 0.0750 kilograms. 57 centimeters? Well, there's 100 centimeters in a meter, so it would be 0.570 meters per second. Don't get caught up with this one and say, oh, it's divided by 3.6. It's not kilometers per hour to meters per second. It's centimeters per second to meters per second. All we have to do there really is convert centimeters to meters, because the seconds is already there. We multiply those together, we end up getting 0.0428 kilograms meters per second. Now, sometimes we may want to express that in scientific notation. That happens a lot on tests. What would that be in scientific notation? 4.28 times 10 to the negative 2. Good. By the way, if you're like me and you have a little bit of trouble sometimes moving decimal places, then don't write in 0.075. Just go 75 says on your data sheet, it's 10 to the minus 3, so 75 times 10 to the minus 3. 57 centimeters, that's 57 times 10 to the minus 2. That way we don't have to worry about moving the decimal place over the wrong number of places. So whatever works for you. Okay, whatever works for you there. Next question I think we need to go over was 7, is that right? 5, I guess, yeah. 5. 5 says, a 5 kilogram ball accelerates at a rate of 2.0 meters per second squared for 1.5 seconds. I think we said yesterday we added to that it started at rest, right? I think I told you that, didn't I? I meant to tell you that. Pretty sure I did. All right, we're going to say that it starts at rest. Meant to mention it to you. For 1.5 seconds, what's the ball's momentum after the acceleration? This is kind of similar to some of the questions that we did yesterday, except the rate of acceleration isn't 9.81 here. It's 2.00. We've got a mass here. Okay, we don't need to worry about converting units there. We've got an acceleration. We've got a time interval here. And we want to find the momentum after the acceleration. We want to find PF here. It's going to be equal to m times VF, m times the final velocity. But we don't know what the final velocity is. How am I going to find it? How did we find it yesterday? VF squared, VI squared plus 2AD. Yeah, it's not the only way to do it, but it's probably the simplest way. We'll cross off VI because it's 0. VF becomes the square root of 2 times 2.00 times the displacement of, oh, wait a second. We don't have a displacement, actually. That's not going to be the simplest way. You know what, though? I'm glad we did that. Okay, I'm glad we wrote down that equation, even though it's not going to help us here right now. The point that we can make with this, I don't even want to call it a mistake. Okay, the point that we can make with this equation that we tried to use but didn't work out for us is that, look, if we use something that's valid, if we use an equation that is a valid equation, an acceleration equation, we're not going to get the wrong answer. What happens here? We just don't get an answer. That's okay. What happens when we encounter this? Look, we got 2 unknowns in that equation. What do we got to do? Try something else. We got to get VF. We're not going to get it with this equation. Let's try another one. How about A is equal to delta V over delta T? Let's try that one. Delta V becomes equal to A times T. 2.00 meters per second times a time of 1.5 seconds gives me a change in velocity of 3.00 meters per second. What was VI? 0. If VI is 0 and delta V is 3, then what's VF going to be? 3. So let's plug in the value of 3.00 for my VF here. And I'm going to end up getting a final momentum of 15.0 kilograms meters per second. Don't worry if you do something like I just did up there. Don't worry if you write down an equation that doesn't work out for you, as long as it's valid. Don't use V equals d over t here. You can't use that because it's not a constant velocity. But you can use any of those acceleration equations. If it gets you the answer, it's the right answer. Worst case scenario is you end up with 2 unknowns and you have to try something else. All right, let's take a look at question number 7 now. So it says a 1 kilogram rock is thrown up into the air from ground level at a speed of 8. Ball travels up to a max height, then returns down to the ground. What's the momentum as it strikes the ground? I think it might be a good idea in this question to draw a picture. Do whatever you got to do to visualize this, to see the question. And again, I think the best way to maybe do it in this question is to draw that picture. We've got that rock that has a mass of 1 kilogram thrown up into the air with a speed of 8.00 meters per second. That's going to be VI. It goes up to a maximum height, and then what happens when it reaches that max height? It stops, and then what happens to it? It drops. It comes back down. What rate does it slow down at as it's going up? Neg 9.81. What rate does it speed up at as it comes back down? Neg 9.81. So if it slows down at a rate of 9.81 over a certain distance, and it speeds up at a rate of 9.81 over the same distance, isn't it going to be moving the same speed when it hits the ground as it was when it took off? We want to find the momentum as it strikes the ground. We're going to say P is equal to m times v. The mass here is 1 kilogram, and the the velocity is negative 8.00 meters per second. Same speed that it had when it took off. So my final momentum is negative 8, or we could say 8.00 kilograms meters per second downward. Could we have found VF mathematically in this question? Let's say we didn't recognize that it was going to be the same VF. Just for whatever reason, that just kind of slipped past you. Could we have found VF mathematically? Sure we could have. We could have used that equation that we used a bunch of times yesterday. VF squared is equal to VI squared plus 2AD. We'd be looking for VF here, right? VI would be, well, VI would be 8, right? A would be neg 9.81. What would the displacement be as it goes up and then comes back down? 0. It's like running around the track outside. Your distance covered around the track once is 400 meters. Your displacement is 0 because you end up back where you started. If my displacement is 0, then this entire term disappears, and I end up taking the square root of 8 squared to get VF. What does it end up equaling? 8. I mean, if you spot that it's going to be 8 right off the top without doing that math, then that's great. If you don't, then do the math. You get the same thing. Let's take a look at number 8 now, too. A 1.5 kilogram rock thrown up into the air from ground level reaches a max height of 7 meters, then returns to the ground. What's the rock's momentum after it strikes the ground? Or as it strikes the ground, I should say. Let's draw the picture for this one again as well. The mass of this thing is 1.5 kilograms. Max height, we're going to say that's h. Let's just label it on our diagram here. Max height is 7.00 meters. We want to find the momentum down here as it strikes the ground. We can't use VF squared is equal to VI squared plus 2AD for this entire trip because we don't know what VF is, nor do we know what VI is. We need to find VF, and we don't know what VI is. So again, that equation doesn't seem to work out for us unless we do what, Nick? Question? Okay. Go ahead. Exactly. Not 1, 0. Yes. That's exactly what we're going to do, Nick, is we're going to chop it in half. We're going to analyze not this entire trip, but we're going to analyze only the trip downward. If we do that, what's the initial velocity here as it starts moving downward? 0. If VI is 0, then we can easily find VF. We're going to say VF is equal to the square root of, this disappears, the square root of 2 times neg 9.81 times the displacement of negative 7.00 meters. So my height is 7.00 meters, my displacement is negative 7. When I do the math on that one, I get a final speed of 11.71921 meters per second. Of course, the velocity is negative 11.71. When I multiply that by the mass, I get a final momentum of 17.6 kilograms meters per second downward. That make sense? Don't be afraid to try things like that. I mean, Nick made a great point there, right? Let's chop it in half. Are we allowed to chop it in half? We can chop it into thirds if we want, or chop it into 57.5 sections if we want. It's not convenient to do that, but we're allowed to do that. It's convenient to chop it into two sections, so let's do that. All right, I'm going to give you a multiple choice question to work on right now. You have it at the back of your worksheet booklet, but I'm going to put it up on the board as well. It's multiple choice question number 2. It's a relatively straightforward one. I'd like you to take about 1 minute to work on this. Just pay attention to the little things in this question, because there are 1 or 2 little things that you have to watch out for, otherwise you'll make a silly mistake. Other than those little things, it's not a bad question. See what you can do, okay? We'll check it over in about a minute. All right, let's take a look at the question here. For those of you who are finished, those of you who aren't finished, just kind of drop what you're doing and focus up here. We got a super tanker loaded with oil, mass. Here's a mass. Okay, as soon as we see that, if you want to write that down, that's okay. If you want to do it later on, whatever works for you. Super tanker has a cruising speed of 20 kilometers per hour. Let's draw special attention to that one because it's kilometers per hour. You know what the thought that just came to my mind as I saw that was? Divide by 3.6. Sometimes that comes to my mind right away. Sometimes I think of it later on. Write it down whenever it comes to your mind. Okay, as soon as it comes into your mind, write it down. Even if you're reading through the question and you're past that, and all of a sudden you think 3.6, oh, 3.6. Okay, I better go back and write that in just in case I forget that thought that just came to my mind. All right, that's also going to be the speed or the velocity. We got a time here of 32 minutes. We've also got a time here in minutes, okay, which obviously we're going to want to convert to seconds if we use that as well. We're going to find the momentum of the supertanker at cruising speed. So let's say P is equal to m times v. And the mass is 1.00 times 10 to the 9 kilograms. And the velocity is, what is it, 20? It's not 20. We've got to convert that to meters per second. We divide that by 3.6. I don't even have to think about that now, because when the thought came to my mind, I wrote down divide by 3.6. Now I can just go do it. When I divide that by 3.6, I end up getting a speed or a velocity of 5.55556 meters per second. Notice I've gone to 5 decimal places there. You should always go to 4 or 5 decimal places when you're doing a conversion. Don't round it to 1 or 2 decimal places. When I multiply those two numbers together, I end up getting 5.56 times 10 to the 9 kilograms meters per second. Now, how do they want that expressed? First of all, it says b times 10 to the w. What's the value of b? Well, that's the base. That's this part of it right here. Here's what a lot of people will do at this point. You go to fill that in a 4-box numerical response answer sheet, and people will say, oh, the answer is 6. Why do you think people put 6? Yeah, they think it's a single digit, right? B, it's not B point something, it's just B, so it's a single digit. But what do they tell you right below there? We want the value of B, and B is a 3-digit answer. So what would I fill in there? Not 6. I would fill in 5.56. The 9's irrelevant here for us. We just need to be able to fill in the base here. Does that make sense? Okay, let's do one more example problem today. It's a little bit different. Shifting gears just a tiny little bit on it. It's still on momentum, but we're going to learn about a technique that we use to solve a problem where maybe it looks like we're not given quite enough information to solve it. This one says an object has a constant momentum of 245 kilograms meters per second. We want to determine the momentum of the object if its mass decreases to 1/3 of its original value, and the force causes the speed to increase by a factor of 4. Normally, we would want to find a momentum using P is equal to m times v. But we don't know what m is, and we don't know what v is. So how do we do that? Well, we use a technique that I call variable value changing. We're going to change the value of these variables, mass and velocity, without knowing what the values were to begin with. Here's how we're going to do it. We're going to write down an equation that's relevant. Of course, our relevant equation to this problem is P is equal to m times v. That's what we'd want to use to solve the problem if we had m and v, so write that down. We're going to call that PO, my original momentum. This is what I start with. m times v. But we also know the number that I start with. It's 2.45 times 10 to the 2. So this is what I have. Nothing new here. This is just writing down what's given to me in the problem. My equation is m times v. Its value is 2.45 times 10 to the 2. My new momentum, the momentum that it becomes after I make changes to it, is not m times v. It is mass times velocity, but mass is not m and velocity is not v. If the mass was m, anybody tell me what the mass is now? 1/3 m. So we're not saying that momentum is 1/3 of the mass. No, it's not. The momentum is mass times velocity. We're just saying the symbol that we're using, that we used for mass was m. Now the symbol that we're using for mass is 1/3 m. If the velocity was v, what's the velocity now? 4v. Let me ask a quick question. Micah, what's 1 times 2 times 3? Good. Let me worry there for just a second. Patrick, what's 2 times 1 times 3? Good. Sydney, what's 3 times 2 times 1? Oh, boy, tough questions today. You guys are getting better and better at them, though. The point that I want to make with that is it doesn't matter what order we multiply those numbers in, we get the same answer, right? What's 1/3 times m times 4 times v? Well, it's the same thing as saying 1/3 times 4 times m times v. Would you agree with that? Same thing. I'm just simplifying a little bit, pulling the numbers out in front, okay? Now I'm going to simplify it a little bit further and multiply those two numbers together. I end up getting 4/3 m times v. Here's the crux of the problem, though, right now. I know what the value of mv is. We just wrote that down. mv is 2.45 times 10 to the 2. So I'm now going to sub in 2.45 times 10 to the 2 for m times v. But we know the value. That's the value of m times v that was given to me in the question. Now let's just sub it in and multiply 4 times 2.45 times 10 to the 2 and divide that by 3. When we do that, we end up getting 326.666, or 327 kilograms meters per second. Might seem a little bit hard at first, but when you take a step back from it, it really isn't. Step number 1, write down what you've got. In a sense, it's like givens. Right? Write down what you've got. The equation, m times v. The value, if you happen to be given a value, 2.45 times 10 to the 2, written right in the question, first line of the question. And then let's sub in our new value for mass. Well, we don't know a number for it, but we do know what fraction it is of what we started with. Let's sub in a new value for the velocity, same thing. Let's bring those numbers out in front, and then let's sub in the original value that we had for m times v, and we get our answer. Does that make some sense? All right, you're going to have a couple of questions to work on in class over the next few minutes here. You've got about 8 minutes to work on these questions in class, and you probably should be able to finish up both of those questions. In addition, you're going to have some check and reflect questions at the end of the section in your textbook to do for homework. They are on, a couple of them are on this stuff, but most of them are on the stuff that we did yesterday and for homework last night. We will have a quiz on Monday, but the quiz on Monday will end at basically what we had for homework last night. So you won't see a question like this on your quiz on Monday. Does that make sense? All right. These are the questions that I'd like you to work on right now. The questions for homework from your check and reflect questions are on page 453. Numbers 1 to 2, 5 to 9, 11, and 13 to 16. One little One little thing that I want to point out in question number 1 here, okay, before you really get going on it. At the bottom of that question it says, what's the momentum at the speed of the bullet increases by a factor of 3/2 and its mass decreases by a factor of 3/4? My new value of the mass is not 3/4 of the old value. My new value is what? If it decreases by 3/4, it decreases to 1/4, right? If it's decreased by a factor of 3/4, it's now 1/4 of what it was. The numbers we always want are the number that it is, okay? Not the number that it's decreased by. So we're going to use 1/4 instead of 3/4 in there. Unfortunately, when you do that, you're not going to get the answer that they give you here because they did it incorrectly. The answer is wrong here. So I can't remember what the answer is, but when you do that and you get a different answer than that, don't panic. You're probably right because they're wrong. All right? That's it for today. Let's finish those up. Those 2 questions at least up right now, and then let's finish those check and reflect questions on 453 for homework.